Okay, here I am, Jay Fidell. We're doing research in Manoa. We're talking about broadband in rural Hawaii with Magdy Iskander and Astosh Das. Magdy is a longtime professor at the School of Engineering at UH, and Astosh is a master's candidate there. And they're here together because they're working on the same project, at least one project. And this project is about broadband in rural Hawaii, which is very important to Hawaii, and its growth and development and its nature as a unified state, very important. And you guys have a grant now, so tell us why the grant, what the grant is, what you're going to do.
Well, to begin with, wireless connection is essential to every day of life, not only for communication, but also for health, for job opportunities, for education. So availability of wireless network, reliable and broadband wireless, is an essential part of life. The problem we have here is it's not economically viable to develop this reliable and broadband wireless communication system in rural areas. We can't afford having the required number of base stations. Therefore, there is a need to develop new technologies that will meet the specific challenges that deal with or unique to rural areas. And we have plenty of this in Hawaii. In order to develop a low-cost and reliable and broadband wireless for rural areas, we have to look at the entire system and see what can be done, what can the technology do, not only from the physical layer, from the antennas and propagation and the radio area point of view, but how we can do it without interfering with the already set standard in the wireless communication upper layers. I mean, these antennas and this wireless system had to go through the internet and interface with different layers. So how can we bring in technology in the physical layer, in the antenna and radio area, without really interfering or disturbing the already existing standard in the higher layers? And that is really a key to our grant. We found a way to do it.
Okay.
So go ahead.
You have a slide to show exactly what these layers are?
Yes. So when talking about, if you look at this first slide that showed that the challenges, the specific challenges, communication in rural areas, not only the terrain, but limited number of base stations, as you can see, the power requirement, the bandwidth, the connectivity, reliability, and the range, and so on. That tells us we can no longer use the well-established technology, namely we have the antennas radiating uniformly in all directions. If the antenna radiates uniformly in all directions, the power doesn't go far enough while you are communicating in a specific direction. So we need something called directional antennas. And in order to have directional antennas, you have to see where the antenna is, or we have to find out coordination between where the antenna is looking versus what the upper layer are processing. And that's why there has often a disconnect between what we develop in the physical layer and what we end up in the upper layers. So what we have done, if I can show you in a second, in one of those.
Okay.
No, I'm going to continue on. What's going on here? Yeah, maybe I go this way. Here we go.
There it is.
So we are trying to use something that's called cognitive networking. Cognitive networking has a wide variety of technologies involved in it. It has directional antennas, namely antennas that focus in a specific direction. It makes use of what we call propagation modeling. You have to understand the channel if you have a mountain, or if you have land-sea transition. All of that requires specific path loss and problematic problem in connectivity in the wireless communication system. And we have to find some available spectrum. The availability of the spectrum, the path loss aspects of it, the antenna technology aspect of it, if we can coordinate it, we'll be able to develop a low-cost, high data rate wireless communication system that can be applied over extended ranges, namely in rural areas.
So this is all about radio.
It's beyond radio. It's radio signal processing, it has networking in it, and it has propagation modeling in it.
This isn't being done elsewhere.
No, that's, you see, nationwide, there is an initiative called EARS, E-A-R-S, which is Enhanced Access Radio Spectrum, Enhanced Access to Radio Spectrum, trying to provide wireless high data rate wireless communication capability to every house in the United States. And the way we're doing this is they already allocated the spectrum, they sold the spectrum, everybody owns portion of the spectrum, but that spectrum is not being used on a continuous rate, usage during the day, 7/24. So they have to have the radio smart enough to go and see and sense without interfering. That's the catch. To get the radio to see what spectrum is available when, and use these available channels in order to establish communication system. So we are putting more smarts in the radio. It's not just a receiver with antenna radiating all over the place uniformly. We're putting a smart. It has a spectrum sensing. It has environment sensing, namely the propagation modeling, and has directional antennas, and then coordinating all of this in order to facilitate long-range broadband wireless that is suitable particularly for rural areas.
Brand new. It's brand new.
There are national effort going in this. What is brand new about what we are doing is the fact that we are going to do it in the physical layer down there in the antenna and the radio area without affecting the upper layers. There are nationwide, worldwide, they are trying to do similar things. The cognitive radio is a very broad area of technology. But they always say, if we do this in the antenna area, this is the corresponding corrections they have to do in the other upper layers. Here we're trying to say, no, we're going to do it in the physical layer without affecting the upper layer, and that's what's unique about what we're doing.
What's the net effect at the end of the day? Do you deliver a signal as fast and strong as you would on cable?
That's the ultimate objective, but at least it's a high data rate wireless communication system that can help people access health need, job finding need, the commerce need, shopping and all the stuff, as well as the communication needs. In this slide that if you can see here, in this slide you see the varying component of our technology. We're talking about directional antenna to the left, we're talking about propagation modeling in the center, and then cognitive spectrum sensing to the right. That's how to interface with the upper layer to the right. Basically, in the cognitive spectrum sensing is trying to find the gaps of available spectrum in the specific channels and use it when it's not being used, and trying to do this with minimum interferences with other users. That's very important. So these are the technologies that we're trying to develop. And if I may show you one more slide here. This is the directional antenna part. This is the propagation. We're going to get there. Here is the upper layer. Much of our work is in this lower layer here. It's called physical layer. And we're trying to do all of...
So it's a layer of what?
Oh, the layer of technologies. And this layer of the people, in order to help understand how communication system works, they develop this layer of technologies. Most of the hardware is in the physical layer, in the bottom layer here. And the upper layer are mostly software kind of layers. And this is very important, the data link layer, where it shows where the antenna is looking, where the channel is available, all this upper connection to upper layers. And then you have the networking layer and transport and applications and so on. So we are doing most of our development in the physical layer with minimal of no impact on the upper layer, and that's why we call it low cost, that is suitable for rural areas kind of communication system.
Okay, so sounds to me like this is going to be huge.
Well, if you, we got some evaluation, of course, from the National Science Foundation, and among the words they use is a transformative.
Yeah, that's
with,
major.
I mean, they use this word, transformative, with major impact on facilitating broadband wireless communication in rural areas.
Okay, so how much has been, how much of this technology has been given to you, and how much are you designing from the ground up?
Well, we have been previously working on developing directional antennas for the Army. So we have been funded for the last couple of years from the Army to develop directional antenna, again, try to focus the beam and so on. In their case, for DoD and for Army applications, they don't have base stations. The base stations are moving. Therefore, the communication has to be adjusted between the base station and the mobile unit all the time. And directional antenna is way trying to find that. So we're trying to design for the Army low-cost directional antennas. And actually, this is the one antenna that we just showed you. Yeah, here. This antenna here. So we are actually applying for a patent on this. There are very significant requirements on operation of this antenna. Not only it is narrowband, namely directional, but also dual polarization. So it can pick up the signal regardless of which direction the signal is coming for. And it's also broadband, so you can operate over a wide variety of channels. So there are, and the low cost. So there are specific, very desirable characteristics. And you can see here is the radiation pattern. As you can see, the antenna is very directive. And we actually developed this, and we tested in our labs. And if I may mention, some colleagues from the Army are coming here within the next couple of weeks to help us conduct, or to work with us on conducting some of these tests. You can see transmit, receive, beam forming and beam steering. You can do that. That increases the link reliability, better reception, but it's also dual polarization. That's very important. So it can pick up the signal, and it is reasonably broadband. So that's one area. The other area that we would like to talk about is University of Hawaii is really uniquely qualified to do propagation modeling.
What is that exactly?
You remember when the wireless communication started, the wireless companies or the, what you call that, the service provider used to drive on the street to pick up signals in order to see signal strengths and where to place base station and so on. Now we can do that through computer simulations. Our team, and in particular our colleague, Dr. Yun, who is in our department, Hawaii Center for Advanced Communication, came up with the idea that he can use Google images. So from Google images, which are normally two-dimensional images, he was able to build three-dimensional geometry from shades and things like that, build the three-dimensional representation of the building, as you can see on the slide here. And from there, try to predict propagation modeling, signal strengths in different areas and so on. That turned out to be extremely important because now people can download cities, and we have downloaded cities, and try to see where actually to provide base station in order to provide, to build base station to provide uniform coverage in the entire city.
The nodes.
The nodes. Exactly.
Is this related to mesh technology?
Well, it's not, but mesh technology can benefit from propagation modeling.
Yeah,
Again,
okay.
in the mesh technology, you need to know where to put the base station, and or at least the transmit receive unit, and they can benefit, of course.
So
from
these
the
are like
propagation
topographical maps of the buildings?
yeah,
and
from
with
Google
that,
Maps, and
yeah.
then you build around it the RF signal strengths, as you can see in the red areas and green areas, the lines that you see in between buildings here.
What happens if they build a new building, brand new building?
Well, you have to get a Google managed map and
To
try
update
to,
it.
to update. Yeah, very good point. And update it, exactly.
Yeah.
So we are implementing all that in the rural. How this relevant to the rural area is relevant because you have mountains, you have land-sea transition with some unique propagation characteristics, and we actually modeled all of that. We were funded by the Office of Naval Research a competitive grant for 3 years to develop this propagation modeling capabilities.
My head is spinning, Magdy. I mean, with all the
I'm sorry.
possibilities. No, the technology I can get to, but the possibilities are astounding, transformative even. That's Magdy Iskander and Astosh Das from Holmes Hall, from the engineering department at UH. We're talking about research in Manoa. We're talking about broadband in rural Hawaii and much more. We'll be right back after this message.
Hi, I'm Ethan Allen. I'm the host of Likeable Science on ThinkTech Hawaii. We talk about why people should like science, why science is actually fun, how science is a dynamic and vital part of everyone's life, why everyone, every man, woman, and child on the planet should really know science, should love science, should be familiar with science. So it's a great show. People come on here and have interesting conversations with us. They tell us why they do what they do, why they love it, why we should love it too. I hope you'll join us every Friday, 1 to 2 p.m. And of course, you can see it anytime on YouTube. Aloha.
Okay, we're back, we're live, we're here doing research in Manoa, talking about broadband in rural Hawaii and more, with Magdy Iskander and Astosh Das, both of the School of Engineering. Magdy is a professor, been there a long time, and Astosh is a master's candidate, learning every day. I wish I were you. A new world. Okay, so we got the general idea that what you want to do is use wireless to deliver high-speed broadband anywhere, even over great distances. And you know,
cost effectively, reliably, and without interfering with upper layers and messing up the set standard in a communication system.
okay.
So you can integrate with existing system while using high-tech technologies to meet your needs in the urban environment.
This is really smart. This is,
If
it
you-
deals
if-
with all the challenges.
If you can do it.
If you can do it.
If you can do
Well,
it.
you believe you can do it.
I mean, this is slideshow that how we are going to do it.
Well, it works on a slideshow anyway.
Yeah.
Okay, but you know, just to take a moment and look at the possibilities of this transformative technology. Is disruptive an appropriate term? Or transformative?
No, I don't think it is.
It's not disruptive, but
It's
it is
not.
transformative.
It is peacefully transformative.
Okay, okay.
It doesn't interfere, obviously, hopefully, with existing technology.
But you know, I give you a world that needs internet, as you said before. Everybody needs internet because it allows a given community, a society, to live a substantially better life.
Exactly.
All those things, and to be connected to all humanity. I mean, wow. I mean,
It's so required for health, for job, for education, for daily life. Actually, you can't live without an internet.
yeah.
And as we mentioned in our proposal to the National Science Foundation, there are 19 million Americans without high data rate, reliable internet. So there is a need. There are 90 million of us here in the United States that need these services. And commercially, their needs are not going to be addressed by commercial companies because it's not cost effective for them. So we have to find a way to develop a technology that specifically address that specific need of people in rural areas. And we have considerable amount of this here in the state of Hawaii.
So if I want internet in Dankuda, Nepal, this would help me.
Absolutely.
I could get it from Kathmandu,
Yes.
across the mountains,
Yes.
with repeaters and all the equipment you're talking about.
Yeah, we found ways because we know how to cross mountains, and using our propagation modeling capabilities, we know where to place this thing in order to ensure connectivity. That's very important. And you can actually gain a lot of advantages by optimizing the location of these either repeaters or the base station, whatever you call them. And we have shown over the years advantages, significant advantage, by the way you optimize the location of a repeater on a mountain or away or in a specific location.
This is great stuff. must be really thrilling for you,
Yeah,
because you're at the cutting edge. You're going to help humanity here.
Well, I hope so. Thank you.
All right. Well, let me go a step further on it then. So, all these elements that you drew out on the chart, on the PowerPoint, you have to create them. You have to make them work. You have to make them work
Yes.
with each other.
Yeah.
You have to build black boxes that will all talk to each other and do what is expected. I imagine some of the black boxes already exist, but some of them don't. And the integration probably needs to be
That's right.
achieved.
That's right.
So how do you do that? I mean, you have a little laboratory somewhere in Holmes Hall with little black boxes talking to each other?
Yes, we do. We'll get to the bits and pieces, software, and we'll come to the software part where Astosh is an expert in that area. But if you look at this slide here, you will find, you're right, the little things that we need to build. First of all, we have something here that is called, I don't know how to point at this, it's called advanced nodes. You see this advanced nodes here. What's the advanced node? You remember the antenna I showed you, the directional antennas? Here are the directional antennas. There are 6 of them. Okay? And these arms there or fingers there, these are the radiation pattern moving around, not simultaneously, moving around to cover certain areas. So these are the advanced nodes. Yes, we do have these antennas built, and we have already measured them, and we are satisfied with the characteristic we obtained.
It goes 360 though. I thought this was directional.
It is, because you don't operate them all at the same time, but you have the capabilities to rotate.
Any
so
direction.
that is where the software, that's the beam steering and the selecting of which sector you should go to, depending on the propagation constant information.
But what I hear you saying though is this is a central unit,
Exactly.
and it can broadcast in any direction,
Yeah.
or every direction. It could be in Kathmandu and cover all of Nepal by wireless.
Yeah, in different.
You have to
in
aim
sector,
it. You
yeah,
have to aim
exactly. I have to aim it, and now you can see the importance of the coordination.
Yeah.
Because you might be aiming in certain direction, and the upper layers are looking at it. Because the whole system is built based on an antenna that radiates equally in all directions. So you don't worry about that. The antenna is radiating, you are picking up signal or not, and that's how if you have a channel or you don't have the channel. Here you have to there are some coordination that is required in order to make that work.
Okay,
So we have this, what we call these advanced nodes.
This already exists.
Yes.
If I go into your laboratory, I can find one.
Yeah, you will find the antennas, and yes.
Okay,
we
what
do. And
else
we
you working
delivered
on?
certain number of them.
Actually, I see 2 of them. They're talking to each
Yeah,
other.
because there are 2 advanced nodes, for example, on the different areas in the coverage in the rural environment. You can't just have one of them, but you can see every one of them is responsible for a bunch of mobile devices, whatever any mobile device. So they coordinate among them. So you can have 2, you might end up having 3, depending on how challenging the propagation environment is. But you don't have to have these base stations scattered all over the place to serve this mobile. You can only have 2 or 3 of these covering the rural areas, taking advantage of knowledge in the propagation modeling that I mentioned earlier, and the path loss and all these capabilities.
So what's the range of one of these directional devices?
It's a high gain. The specific gain of these antennas, all what I can tell you about, is about 20 dB. So it's a very high gain compared to regular antenna, which is only few dB.
So how far would that go? Would it go 100 miles?
Yeah, if you are putting hundreds of watts
Okay.
and cooking bunch of birds in between, right?
You
If
don't
you're
wanna
putting
be-
a kilowatt
you don't
and
wanna
killing
be
the
in
birds in between and sacrifice few human beings there, in a microwave oven, it will work, yes. It depends on how much power you put in it.
Okay.
That's the point.
Okay,
really.
okay.
So this is really the key slide. That is the key technology that we proposed to the national. We said we integrate our directional antennas with the propagation modeling and the software end of thing of how to use this information in order to, we are sniffing. Oops, you lost your You got too excited.
Yes, I'm very excited about this. So, how do you have your mic on? I want to be sure you have your mic. Feel it? Okay, wait,
I feel
it's
it.
all engineering.
I don't know if the mic is still there, but
Okay,
I feel something
I
here.
want you-
Yeah.
Okay, we're fine. So, it seems to me that you could cover a large area by repeating these directional.
Exactly.
So you have two on this
Yeah,
chart.
exactly.
But if you wanted to cover the whole area, you could cover, and the software would be the thing that makes it
Connects them.
work right.
Yeah.
The right signal, the
Yeah.
right direction, all that stuff.
Exactly.
So, look, can we talk about the software?
Sure.
Can I make this software myself?
No.
What does
no.
it take to make this software?
It's a very high-tech
Yeah.
software because, as you know, you have to very carefully adjust the threshold signal detection of the receiver. If you set it up too high, you will miss signal. If you set it up too low, which means we're going to see if the
Yeah.
channel is available and it's not available, you're going to cause interference. So that's one thing.
Yeah.
And you have to set it up also in such a way to direct the antenna to get the high signal to noise ratio, because that minimizes the number of bits that you need to detect in order to establish a reliable communication channel. So there is a lot of variable and parameters that you have to adjust very carefully.
Is it
and
automatic?
It will be once you establish the right
Yeah.
software, and it's a lot of trial and errors and a lot of adjustment depending on the environment. Setting all these parameters would be specific, I guess, to the propagation
right.
environment.
You're prepared. You're coding this software, aren't you? I can
Yeah,
tell
yeah.
with your exuberance about it. What language is it in?
MATLAB. We're using MATLAB.
MATLAB.
Yeah.
Okay, this is
That's-
a sophisticated science language.
Yeah, it's kind of science language where you know like bits of coding, so you can use that in designing this kind of project.
Okay.
You're using MATLAB, you're using OpNet
Yeah,
also
OpNet.
for the networking part of it as well.
Do you need a sophisticated computer to run this software, or will it run on my PC?
Well, ultimately, the software will run on this
the
advanced
laptop. There's a
on the
PC laptop.
advanced
Node.
nodes.
Yeah.
So the advanced node should
Oh.
have enough computational power
Yeah.
to run all this in real time. Yes,
And make all
That's-
those dynamic adjustments they
Yeah.
have to make.
exactly.
So nobody has to actually tweak it. It just goes.
Hopefully not. If it has to tweak it, lose its value.
Okay, so you're designing black boxes. You're integrating black boxes, new black boxes with old black boxes. I mean,
Yeah.
ones that already exist, and then you're connecting them with this software that will run hopefully by itself on a PC,
Yeah.
not a big PC, and correct everything that needs to be corrected. And wow, so if I'm in Kathmandu and I'm trying to deliver signal to a place say 100 miles away through the mountains, what's it going to cost me? Any idea? It's just going to be expensive because you're talking about rural areas, so by
And-
definition they have no money.
Yeah, and that is actually a part of the title actually of our proposal, low cost. But the low cost is coming from the fact that we're replacing this old hardware, the radiating homogeneous in all the with directional antennas. We're replacing all the need to integrate with the higher level with having these focus units that can mobile actually. Oh, by the way, I forgot to mention that these advanced node are actually mobile units.
How big?
So, I mean, it's like a base station, like have a transmitter
This
on it, very bigger than that, but they are mobile, so you can move them from one location to another in order to continue detect available channels or optimize communication in a specific.
Are they intended to be moved, or are they intended to be stationary for a long time?
No, we propose it as a movable ones. There is no
Okay.
reason why we should make them movable in order to address a specific need as they come.
So when you say movable, I just want to I love this actually. When you say movable, you mean it's a box. It's got antenna-looking device, things on it. You plug it in for power somewhere. You have to have power.
Or battery operated.
Or battery,
Yeah.
AC or DC doesn't matter.
Yes.
And then it's going to receive and send,
Yes.
right? Both.
Yes.
and it's going to have a computer that helps it do all that.
Yeah.
And so it's a unit that could go anywhere.
Yes.
Top of a mountain, bottom of a mountain, in a small town, in Kathmandu, whatever. So it's essentially going to connect with other like antennae in other locations
It can
and cover the area.
It either couple with a mobile units all over the place, or it communicate with another advanced node to enable some more transferring some of the units, the mobile units, to the other, coordinate the activities between the advanced nodes.
So that's really sophisticated. It's not just this antennae, this antenna talking with like antennas. It's talking with other devices as well. All kinds of devices. Even devices.
Software now, integration of software in antenna design is what we call a smart antenna system, is a crucial part of the technology. The antenna by itself is just an antenna by itself.
Yeah.
But integrating it with software capability, beam steering capability, beam forming capabilities, and all these things, really key in advancing the wireless technology.
Wow. Okay, that's Magdy Iskander and Astosh Das from the School of Engineering at Holmes Hall, Manoa. We're talking about research in Manoa. We're talking about broadband, fantastic, transformative broadband for the people in rural areas. We'll be right back after the short break when we are going to ask him again how much it's going to cost.
Hi, my name is Seymour Kazimirski. I have a show called Seymour's World on ThinkTech Hawaii. Our show is about opening minds and facilitating conversations. To tell you the truth, I have no idea what we're going to be talking about. I have no idea who our guests are going to be, but I guarantee you we're going to have lots and lots of fun. Aloha from Seymour's World.
Aloha, my name is Carlos Juarez, and I host Global Connections here on the ThinkTech broadcast series. We broadcast live every Thursday from 2 o'clock and also on Olelo 54. Please make sure to tune in and join us. We'll see you there.
We're back, we're live, we're here doing research in Manoa. We're talking about broadband in rural Hawaii and many, many other places. We could make a list, it'd be an infinite list of all the other places, with Magdy Iskander and Astosh Das, both of the School of Engineering in Holmes Hall, just as you make that left turn up East-West Center Road. They're there.
That's right.
That's a funny statue out in front of it, very high-tech looking red statue.
Orange looking.
Orange, sorry. So this means that with this device, I'm going to ask you how close you are to the solution, but with this device, you could sort of light up any area. And if I took a small town and I wanted to get the signal from another town or city nearby, how much would it cost me to put it in to service, say, a population of people by wireless in that town?
We need to know initially how many of this advanced unit we're going to need.
Depends on the size of the town.
Depending on the size of the town, and based on that, multiplied by, I would estimate, $1,000, $2,000 per one of this unit. Again, the cost here is in the software development, in the smarts you put in the system.
Isn't that something?
Yeah, the antenna technology, we develop it and we know it is low cost. We already have that. Propagation modeling, collecting the information about the channel, integrating that, and developing sophisticated software is going to be really the heart and soul of the system, is a software controlled system.
What I hear you saying, though, is as time goes by and the hardware becomes even more sophisticated, because when you put it out in the field, you're going to learn a lot.
Yeah,
and you're probably going to think of more things you want to do. So now, this antenna would be more sophisticated yet. But you have the solution inherent in the software, and you can tweak the software and put a more sophisticated piece of hardware, and it's not a big deal. You can make it bigger, more powerful, once you get to stage one, in doing this.
As part of this, actually, we promised that we will have a test bed in the Big Island. So part of the NSF funding will go toward having a test bed to see this coordinated detection and establishing of the communication channel on the Big Island. So it's going to be very exciting.
Oh, it is.
I mean, when we started our discussion, you mentioned that there was some effort in the past to establish high data rate and how data rate communication system in the Big Island. I think that's going to be ultimately the realization of that.
Yeah. Well, I remember the name of the fellow who worked on it. It was Admiral Kahuni, who was also a trustee of KS at the time.
Yeah.
Anyway, so you know, I think people need to know about how this grant thing works, how you get a grant like this, what a grant like this covers, how central is the grant to the work. How do you actually go through the grant process, and once you get the grant, Magdy, what's the relationship you have with the granting agency? In other words, it sounds like they're actively involved in working these problems with you. No?
Yeah, okay. The grant is part of the EARS program at the National Science Foundation. This is the Enhanced Access Radio Frequency Spectrum. It's a national vision by the President Obama administration. It's very competitive, which means they fund 10% of the submitted proposals. And to give you an idea how many proposals, I think they received about 200, I think 197 or something.
And it would be from applicants like the School of Engineering?
From all over the country. So they get...
From outside the country too?
No, National Science Foundation need to be inside the country. So you get, you know, but you get that, the Stanford and MITs and UCLAs and all these guys are jumping in with those both feet. And all what you need is out of this 200 that you support 20 or 21 or 22, whatever the number was. So it's very, very competitive, and you have to come up with really unique idea. It can't be incremental. It can't be easy to realize. It has to be something that will provide real benefit and visionary and transformative, as they called it.
So give me an example of one of those ideas that would have appealed to the National Science Foundation as an innovative, creative idea, distinguishing the University of Hawaii from, say, other applicants.
Well, we actually have more than one grant from the National Science Foundation. So I'll give you an example of what we have. We have this one here about establishing wireless communication in rural areas, number one. We have another one about the stethoscope, the cardiopulmonary telescope. That's a device that can be used to measure vital signs and changes in lung water content.
Non-invasive.
Non-invasively, we have patents on this, and actually they published something in IEEE Spectrum. I don't know if I sent you the link about this today. It came out in IEEE Spectrum, an article about the cardiovascular pulmonary stethoscope of the University of Hawaii.
This is great. That's really transformative, for sure.
Yeah, and so all of it, and you see people calling it, I mean, people in the medical profession calling it the holy grail of the medical devices.
I think so.
I mean, they are quoted in the news as it is the holy grail.
I remember Oceanit. Oceanit designed a bed. I called it the magic bed.
Yeah, I remember.
You lie down on the bed, and it would take, you know, your heart rate and your temperature.
That is available, and now they even have devices that you can put on your fingertips in order to measure the vital signs. What's unique about the device that you are discovering the mysteries of the lungs, heart failure, edema, emphysema, sleep apnea. It's all related to changes in lung, critical burns, changes in lung water content. So you have to penetrate inside the body and get signals that can relate to the changes in lung water.
This you don't have to penetrate.
No, ours is the one you penetrate.
Okay.
And really detect changes in lung water, and that's what's unique about it, and sets it aside from any existing. There is no existing device that non-invasively can measure a change in lung water.
That's what I mean. Yeah. So it's
no
outside.
Existing
Never
device.
touches you. You don't have to make a hole in anybody.
No.
The only comparable device is the one that's being developed by Medtronic, and that is as part of their heart pacemaker.
Yeah.
So they have surgery, so it's invasive.
Yeah.
It's implantable device. It's
Yeah.
pacemaker, and there is a device there related to changing lung wall. Ours is non-invasively. I'll send you that.
This is fabulous.
So this is the second one that came from the National Science. The third one, the one that we're doing in discovering new material that has characteristics that doesn't exist in nature. For example, you have conductors. That's obvious. We all know that. But there is nothing magnetic conductor doesn't exist in nature. What's a magnetic conductor? A conductor that reflects electromagnetic waves in phase constructively. So it doesn't exist in nature. When you put a conductor behind an antenna or behind a device, it reflects the electromagnetic wave in opposite phase, so it interferes and kills it. So you have to place them far away. If you have a magnetic conductor, you put it very close to the radiating device, and it enhances the radiation. So this material doesn't exist in nature, but you can artificially build this material. And we have a program using genetic programming to develop this, what you call electromagnetic band gap material. So it is this transformative kind of projects that we have. It's not incremental. It's not that you're making a measurement. It's not that you're optimizing the performance
Really
of the
changing
device.
something.
You have to be changing something in order to surface among the crowd.
These things, well, surfacing is a big word. I mean, what about getting a patent and then giving licenses, and then becoming so wealthy that you can spend all your time here at our studio talking about it?
Well, actually, we're ready for the status quo, for the Cardiopulmonary. We already established a company. So we already have a company. It's called Manoa Technologies.
This is through the Office of Technology Transfer?
Yes, and we are negotiating. We have already the license, but we're negotiating taking the license completely out in the final stages of that. So we have the company. I don't know how much time you have, but the whole thing started from National Science Foundation recognized, you will like that, recognized the status quo project as a commercial kind of project that have some economic. So they put us in a program called I-Corp, which is Innovative Corporation. The I-Corp program is a program that is a commercialization, product commercialization. So they put us through a 6-week workshop in Washington, D.C. of how to commercialize. We were together with 20 other universities for a total of 21, including the Stanford and the Michigan and UCLA's and all these guys. We were among them. At the end of the 6 weeks, they selected the best of show, and we won the best of show.
Congratulations.
As a result, they recommended us to the White House, the Office of Science and Technology Office in the White House, as an example of successful entrepreneurship. And they asked us to start the company, and so we started the company, and they keep monitoring us of how we're moving forward.
Encouraging
the company, exactly. So there are things happening.
That's wonderful, Magdy. No kidding.
But it's different from. But you asked what kind of project that get funded by the National Science Foundation. I'm sure there are other colleagues will tell you stories, but it does have to surface and emerge as unique and innovative and transformative in order to have a chance.
And you'll still talk to me.
Oh, you are my friend.
That's Magdy Iskander and Astosh Das coming down from the School of Engineering on this Election Day Eve to talk about broadband in rural Hawaii and much more. And I'm very impressed with what you're doing, and the fact that you're into commercialization speaks volumes. This is what David Lasner is all about, no kidding.
Okay, all right. Actually, maybe we hope we'll have another chance to talk about we used to call it microwave stethoscope. It's a microwave stethoscope. But when we went through the training period with the National Science, they said people were not going to buy it if it is microwave because you cook food in microwave. And that's why they called it Cardiopulmonary Telescope.
Okay.
That's why it's
as
complicated.
long as it doesn't cook your heart.
Yeah.
But I would like to do that.
It is safer. We characterize it. I'll send you a brochure. And it is safer than your cell phone. The amount of electromagnetic radiation is 1/4 what comes out of your cell phone.
We're going to have this discussion We're going to find out about the stethoscope. And we're also going to find out what he meant when he said safer than the cell phone, because that assumes there is something about cell phones you need to know.
That's right.
All right?
There is a safety standard.
Magdy Iskander, Astosh from the School of Engineering. Thank you so much.
Oh,
guys.
thank you very much.
Thank you for having us.
Coming back.